Ozone is a molecule made up of 3 atoms of oxygen and is mostly found in the stratosphere, where it protects us from the sun's harmful ultraviolet radiation. Although it represents only a tiny fraction of the atmosphere, ozone is a crucial element for life on Earth. And now we have our expert, Ivan Yakinov, telling us about the ozone layer. He's all the way from Russia.
Ozone stratosphere, a layer of the atmosphere between 15 and 50 kilometers, 10 and 31 miles above us, acts to shield and protect Earth's surface from the sun's harmful ultraviolet radiation. Without the ozone, the sun's intense UV radiation will sterilize the Earth's surface. With the weakening of this shield, more intense UVB and UVA radiation exposure at the surface will lead to quicker sunburns, skin cancer, and even reduced crop yields in plants.
Ready? Go ahead. However, near the surface where we live and breathe, ozone is a harmful pollutant that causes damage to lung tissue and plants. This bad ozone forms when sun initiates chemical reactions in the air involving pollutants, particularly a family of gases called nitrogen oxides, released from vehicles and industry during the combustion process, and with volatile organic compounds, carbon-containing chemicals that evaporate easily into the air, such as petroleum products.
I'm pollutants. I'm UV radiation. I'm smog.
Make it like really like.
Are we attacking Alex?
Why are you guys getting so close to?
Oh shit! Alex, you're bad.
We now have Senora Ackerman, all the way from Argentina, talking to us about the chemistry of the ozone layer.
There are natural processes that create and destroy ozone in the stratosphere. These processes regulate a balance of ozone and form the ozone layer. Ozone is created primarily by sunlight. When high-energy ultraviolet rays, UVC, strike an oxygen molecule. No, over there, oxygen. They split the molecule into 2 single oxygen atoms, known as atomic oxygen.
We now have Professor Alpha Theta Epsilon, all the way from Romania, talking to us about the chemistry of the ozone layer.
Okay, the oxygen atom then combines with other oxygen molecule to form molecule of ozone, O3. Because there is so much oxygen in our atmosphere, the ozone-oxygen cycle, as they say, is continuously absorbing high-energy ultraviolet radiation, yes, UVC, and completely blocking it from reaching the Earth's surface. This process creates heat, which warms the upper part of the stratosphere. Here is the reaction. Please observe. They react together, and they create this and that. Here's Cowboy Billy, all the way from Texas, to tell us a little bit more about the ozone layer.
So ozone is very reactive and attacks other molecules in the air, often regenerating oxygen in the process. Also, and this is why ozone is important to us, ozone in the stratosphere absorbs much of the sun's UVB rays, split back into molecular and atomic oxygen. No matter how the oxygen atoms are produced, they almost always quickly react with oxygen molecules, reforming ozone. So, while ozone is continually being replenished, it's also continually being destroyed. If the rate of ozone creation is equal to the rate of destruction, the total amount will remain the same. This is like a leaky bucket. If you pour water in the bucket at the same time and rate that it's leaking out, the level of water in the bucket will stay the same.
Scientists have found that ozone levels change periodically with regular natural cycles such as the changing seasons, winds, and long time scale sun variations. Ozone also responds to some sporadic solar events such as flares. Moreover, volcanic eruptions may inject materials into the stratosphere that can lead to increasing destruction of the ozone.
And here's Professor Camille Kelleher talking about chlorofluorocarbons.
In the 1970s, scientists suspected that reactions involving man-made chlorine-containing compounds could upset this balance, leading to low levels of ozone in the stratosphere. Think again of the leaky bucket. Putting additional ozone-destroying compounds into the atmosphere is like increasing the size of the holes in our bucket of ozone. The larger holes cause ozone to leak out at a faster rate than ozone is being created. Consequently, the level of ozone protecting us from ultraviolet radiation decreases. The ozone destroyed by man-made emissions is comparable or more than the amount destroyed by natural processes. Human production of chlorine-containing chemicals such as chlorofluorocarbons, as shown by Talia, has added an additional factor that destroys ozone. CFCs are molecules made up of chlorine, fluorine, and carbon. Because they are extremely stable molecules, CFCs do not react with other chemicals in the lower atmosphere, but exposure to ultraviolet radiation in the stratosphere breaks them apart, releasing chlorine atoms. Here we have Professor Joya Kelleher talking about a reaction.
Alright, so free chlorine atoms then react with ozone molecules, taking one oxygen atom to form chlorine monoxide and leaving an oxygen molecule.
Go.
If each chlorine atom released from a CFC molecule destroyed only one ozone molecule, CFCs would pose very little threat to the ozone layer. However, when each chlorine monoxide molecule encounters a free atom of oxygen, the oxygen atom breaks up the chlorine monoxide, stealing the oxygen atom and releasing the chlorine atom back into the stratosphere to destroy another ozone molecule. These two reactions happen over and over again, so that a single atom of chlorine acts as a catalyst, destroying many molecules, about 100,000 of ozone. Fortunately, chlorine atoms do not remain in the stratosphere forever. Free chlorine atoms react with gases such as methane, CH4, and get bound up into hydrogen chloride. These molecules eventually end up back in the troposphere where they are washed away by rain. Therefore, if humans stop putting CFCs into the ozone, destroying chemicals into the stratosphere zone will eventually return to its earlier higher values.
And here is Professor Chow on the polar vortex.
The ozone hole is not really a hole, but a thing of the ozone layer over the solar polar region. Every year since at least 1978, there's a sudden rapid decrease in the stratospheric ozone level at the end of the Antarctic winter. During the long winter months of darkness over the Antarctic, atmospheric temperatures drop, creating unique conditions for chemical reactions that are not found anywhere else in the atmosphere. The wind in the stratosphere over the polar region intensifies and forms a polar vortex, which circulates around the pole. The transition from inside to outside the polar vortex creates a wind barrier that isolates the air inside the vortex and also results in very cold temperatures. It's fascinating. At temperatures below -78 degrees Celsius, thin clouds made of mixtures of ice, nitric acid, and sulfuric acid form in the stratosphere. Chemical reactions on the surfaces of these ice crystals convert chlorine-containing compounds like HCl, which is harmless to ozone, into more reactive form.
Go.
Science rules!